Welcome to installment 2 of this 3-part series. In part 1, I recapped this vintage 10 megabyte hard drive, and at the end of that video I plugged in a known good power supply and confirmed that the hard drive would spin up and made no unusual noises. Today I'm going to recap the original power supply that was installed along with this hard disk. This power supply is intended to power this hard drive and a controller board that mounts onto the motherboard of a vintage 1985 Macintosh. This power supply worked fine the last time I tested it, but upon closer inspection I unfortunately found that resistor R4 was broken here on this side. You can even see the little black gunk on the inside, which is the actual resistance part of it itself. So I'm going to need to replace this resistor in order to ensure reliable operation. To do that, we can see that the color bands are brown, black, and yellow, which translates into 100 kilo ohm resistance, and the gold band means plus minus 5% tolerance. Unfortunately, I only have 1/8 watt 100 kilo ohm resistors in my parts inventory, and as you can see, this will definitely not suffice. I need to come up with a higher wattage replacement solution. The higher wattage parts that I do have in my parts inventory are these 1/2 watt 47 kilo ohm resistors and these 1/2 watt 56 kilo ohm resistors that, when put back to back in series, will add the resistances to give us 103 kilo ohms, which is within the upper 5% tolerance of the original resistor. Some of you may be wondering if I truly picked the best wattage rating for my replacement resistors. Then toward that end, I'm going to prove it to you in this circuit simulator. iCircuit is available on the Mac App Store for you Mac users who want to play around with electronic circuits. I highly recommend this software. What we can see here is basically a right branch and a left branch that I'm simulating. On the right branch of this circuit, we see that I have R4, which is the broken resistor in my circuit, approximately 100 kilo ohms in size. And on the left side, I have two resistors in series. I made them both to be the same value initially, just for the sake of our discussion here. We can see that there is 3.12 milliamps going into both the left and the right branch because the resistance, combined resistance, on each side is exactly the same. And the only reason I put 321 volts up here, it's not a practical number, but I put that here because you would require that much voltage to make this 100K resistor dissipate 1 watt. We can see right now it is dissipating 1 watt because the voltage is so high. And over here we see this resistor is dissipating a 1/2 watt, 500 milliwatts is a 1/2 watt, and so is this one. So the combined wattage would be 1 watt, just like this is 1 watt. But it's important that we do not confuse how the wattage ratings add. Technically, in this sense, they add. 500 milliwatts is a 1/2 watt. So 1/2 watt equals 1 watt. So in that sense only do they add. Putting two resistors in series doesn't magically make each 1/2 watt resistor suddenly carry 1 watt. So when we say the wattages add, don't think this 51.5K will handle 1 watt, even though it's a 1/2 watt resistor, and this one will not suddenly magically carry 1 watt because it too is only a 1/2 watt resistor. So always keep that in mind. Whatever your wattage rating is of the resistor is always going to be the maximum wattage rating of that resistor. To further illustrate it, let me change this value to 97K. And then I'm going to change this value to 6K. So that the combined total is still the same 103K, same amount of current going through. So if we were to say, what is the total dissipation, it's going to be 58 milliwatts plus 942. So we're getting a combined total of 1 watt, but you see the problem here. If this resistor, 97K resistor, is rated only at a 1/2 watt, well, we're going to be way, way over its limit because it is actually dissipating 942 milliwatts, almost a watt, in the case of this voltage coming through it. So that's why you have to take great care. Now let's go ahead and do the absolutely practical numbers here. 47 and 56 are the exact numbers I'm going to use. And what do we see here? Well, we see the same current flowing through the circuit. But in the case of the 47, it's dissipating 456 milliwatts, and this one is just over its limit. Now, is that a problem? It's an important question to ask, but the answer is no, and here's why. If we look at the solder side bottom of the power supply and zoom in over here, we see that we have 110 volts coming in here and here, right? You have two wires coming out of your wall socket. And this power supply can also handle 220. So one side will be here, and then the other side of 220 will be here. But since I only have 100 volt power here in Japan, which is basically the same as 110 in the United States, that's all I'm going to be focused on is just the 110. Okay? All right. So we have the broken resistor R4 up here, which goes from this point to this point. And then there's the resistor, which is of the same value right next to it, which is not broken, which connects here and here. And we see that the two resistors are connected to each other at this point. So what is this point? Well, that is 110 volts. So both resistors see 110 volts on them. And where else does the 110 volts go to? If we look, it goes over here to this capacitor. You see the yellow circle. This is a 100 microfarad, 200 volt capacitor. So this 110 goes to the positive side of that electrolytic capacitor, and it also goes to the negative side of this second 100 microfarad, 200 volt electrolytic capacitor. Okay. So where does the other side of this resistor R2 go to? Well, let's trace it out. It goes over and around and down and, positive side. Now wait a minute. 110 goes to one side of that resistor and also to the negative side of this capacitor. And then the positive side of this capacitor goes to the other side of that resistor. Wait a minute. This resistor R2 is connected across the plus and minus leads of this capacitor. It is a bleeder resistor. What about R4? Well, let's take a look. It also gets 110. So where does it go? Ooh, boom. So one side of R4, we can see that here, goes to the positive side of this electrolytic capacitor, and the other side goes to the negative. So R4 and R2, they're both bleeder resistors. What are bleeder resistors? Well, it's like on some of the flyback transformers on compact Macintosh computers. It makes sure that the charge on whatever the thing is that you're talking about is completely dissipated or drained when the power is cut off. You don't want to have residual charge in there that remains for a long time. So in the same case, the designers of this power supply wanted to make sure that when the power is cut, these capacitors did not maintain their charge for a long time, which would be a problem because that would maintain the output. It could potentially be dangerous. There's a lot of reasons why you don't want to do it. And that's the sole purpose of these two resistors, R2 and R4. So what that means is we can also see that they're only going to see 110. They're going to see your mains voltage. So in Japan or in the United States, it's approximately 100 volts AC. So going back to our circuit, we're never going to see 321. We're normally going to see about 110. In Japan, it's exactly 100. But let's say we got something tremendously great, like a super surge of 150 volts. Okay, in this case, how much is R4 going to dissipate? Wow, it suddenly fell from that 1 watt to 218 milliwatts. All right. So even though this resistor, I'm quite sure, is rated at 1 watt, it would normally see less than half of that. And that's fine, because if you have a higher wattage rated resistor and you're going to, say, use only half or a quarter of its rating, it's going to run cooler, and that's a good thing. Now let's take a look at my proposed replacements. 47, okay, 100 milliwatts. 56, 119 milliwatts. So as you can see, when we understand the practical use of the circuit, my half-watt selection of 47K and half-watt selection of 56K are not a problem at all. I'm not going to exceed the wattage rating of either resistor. And in fact, if you look at the physical size of these two resistors, there's more surface area of these two resistors than there is on this one resistor. So using two resistors together can theoretically dissipate in air more heat than this single resistor could. So there's not a problem in using these two resistors, half watt each. Okay, it's now time to desolder this guy. And we can see I put black dots here and here to make it easier to know where I need to desolder. I'm going to apply a little fresh solder on him to make it easier. Wow, look at that. I haven't even fully desoldered it yet, and it snapped right in two. Now, in terms of physical size, here's the stock capacitor, the broken guy I just removed. You can see he's just ever so slightly larger than this half-watt replacement, one of them that I'm going to use. So that's why I suspect this is probably a 1 watt. But again, I'm not completely sure. Either way, as I said, I'm going to use 2 of these in series. 2 half-watts will give me 1 watt of total power dissipation, so I think that's fine. The only thing that concerns me, though, is these cheap resistors that I got from AliExpress China. They are super cheap. And look at the wire. The wire is quite a bit thinner than the stock capacitor wire. For the short distances and the amount of current that's flowing through this power supply, it's probably not a problem for me to do this swap out, at least for now. But probably what I want to do for my next Mauser order is order a single resistor that has a normal thickness on the lead width, not these super thin wires. These are just, with a thin wire like this, you're going to have higher resistance, and that's not good for a power supply. So in the long term, I think I'm going to need to swap it out. For the purpose of testing, I think using the 2 resistors in series will be fine, though. And so it looks like they'll fit just fine like this, and having them raised up like this as opposed to being flat is not a problem. It's a real shame that the wires are so thin, otherwise I'd just be happy to leave it in like this. But when I do buy replacements, I'll also buy another one so I can replace this resistor as well, which is a good idea even though it's not cracked. Now if you're wondering why there's no green color on the bottom here and why everything is covered in solder, well, I can only explain it by saying this was a very early revision board. It's almost maybe like even a prototype, probably put together by hand, I'm quite sure. But I'm going to guess that in later versions of this power supply that they had the regular green solder mask applied as opposed to just covering everything with solder like this. So long as all the traces or the copper is covered with solder, then it's not going to oxidize over time, and through the years, it's protected the traces very well. But still, the green solder mask is really the best approach for mass production products. And just when I was thinking what else could go wrong, something did. Have a look at this. It snapped. This resistor snapped at its base. Great. I'm not even really sure why these white standoffs are here, but for me to use this existing resistor means I'm going to have to remove this standoff and put it closer to the board in order to fix that. I'm not sure what caused it to just snap. Maybe it's just age. I didn't really touch him too much. Anyway, this also has to be repaired. I'm now going to use some steel wool to clean off this little nub here because it's been exposed to air for a lot of years, and I want to make sure it's as clean as possible so that solder is going to stick to it well. Because this spacer obviously doesn't give me enough length to use, I could do away with the spacer altogether, but they must have used it for some reason. So maybe I can cut it in half by putting it on my breadboard here. My thinking in putting it on a breadboard like this is that when I cut it, it won't just fly away. So, let's see if this works or if it breaks apart. I'm guessing it might break. It's such an old piece of plastic. 1, 2, 3. Well, it worked. So I was able to cut it to about less than half, which is just about right because that's all the nub I really need to get through that hole and solder it in. Before recapping any power supply, it's always good to have a frame of reference in terms of the output noise. And since this power supply works already, I know that my measurements are going to provide some useful information. In other words, you don't want to replace the capacitors and have a worse output waveform in terms of noise and ESL spikes than before you recapped it. So I'm going to put 100 volts because I'm in Japan. We have 100 volts AC power, 60 hertz. I'm going to put that in on this side. And I have the 10 megabyte hard drive attached as a load, and I'm first going to test the 12 volt output. I have my scope set up here to be 500 milliseconds per division. We're talking about the horizontal divisions here, each square, and 5 volts per division in terms of the vertical. So this is 5, 10, 15 volts. And when I switch on power, you're going to see how the voltage goes up, and then when the hard drive starts to kick on, the voltage will go down a bit, and then we will zoom in. So what we're seeing here is the peak-to-peak noise that's riding on the 12 volt line. And so each division, each block going up vertically is 200 millivolts, so 200, 400 millivolts, and we can see it goes beyond that. And over here, we're seeing the actual peak-to-peak measurements, which is in excess of even 600 millivolts. So this is quite a bit of noise actually, but a lot of the noise is coming from these ESL spikes, the very, very thin spikes that are riding on top of the actual ripple. Here we are zoomed in on the ripple. So right now we have 1 millisecond per horizontal division. So we got about 1 millisecond between the peaks. So the period is about 1 millisecond there. And our, of course, peak-to-peak noise, including these ESL spikes, is still going up to, I saw it about 632 millivolts, although it is varying. So this is our frame of reference for the 12 volt line. So at 50 millivolts per division for the vertical, we have 50, 100, so it's beyond 100 millivolts. Peak to peak. Actually over here we can see it. I saw it reached about 176 for a little bit there. And again, that's measuring the peak to peak for these ESL spikes, which are higher than the actual ripple. And then for our horizontal, that's 2.5 milliseconds per division. I have my Mauser replacement capacitors here. There's nothing magical about which capacitors to replace first, so I'm just going to randomly choose these two guys because they're the tallest. And don't be surprised if your replacement capacitors are quite a bit smaller than the stock capacitors. These are also Nichicon 200 volt 100 microfarad. Diameter is the same, but the height, as you can see, is just about 60% of the stock capacitor's height. The reason for that is technology has advanced quite a bit through the years. I've marked the polarity of each so I can better see where to put the replacements back on. As always, I'm going to put just a little bit of fresh solder to make it easier to desolder. Put a little flux. Near the bottoms of those two capacitors, we can see little rings around them. Looks like they were glued down. And although this looks like the capacitor may have leaked, I'm guessing it was actually the flux that flowed back onto the capacitor instead, because it looks quite fresh. I will now clean the area with alcohol before putting in the new capacitors. And there's a little plus here and here to show us where the proper polarity should be. And here's our fully recapped power supply. I noticed that this little coil here is a bit wobbly, so I'm going to apply some hot glue to him because it seems like the coil was detached from its base a little bit. That should secure him in place. And then I'm going to put a little bit of hot glue on this one, even though he's a little bit more stable. By the way, I found some cracked solder joints on the flip side of this connector. I applied fresh solder to each of the pins, as you can see here. And now we can test. To be safe, the first thing I'm going to do is test the no load condition. So I don't have the hard drive connected, but I do have the 110, or actually the 100 volts because I'm in Japan, attached over here. And I have it connected up to the 5-volt line. So when I switch on power, we should see roughly 5 volts here on my fluke meter. And we do. So now I'm going to move this over to the 12 volts. And we see no load is 12.32. Okay, now I'm going to disconnect and then connect up to the hard drive. I now have the hard drive connected but powered off. Same scope measurements as I showed you before. I'm going to show you the 12-volt line now. And look at this. With the new capacitors, we're getting a peak-to-peak noise on that 12-volt line of just about 400 millivolts. You can see most of the ESL spikes are absent. What a difference a set of new capacitors make. And now for the 5-volt line. And zooming in on the noise on the 5-volt line, we're seeing something that is not too dissimilar from what we got pre-cap. You can see over here the peak-to-peak value, including the ESL spikes, is roughly what we measured before the recap. So we're seeing most of the benefit on the 12-volt line as opposed to the 5, but that's fine. So long as it's not worse than before, then that's what we're concerned about. Keep in mind that when you're looking at these values, we are driving a very old 10 megabyte hard drive, which has a very old motor, and so this motor load, the inductive load, is going to have a bearing on the noise. And the reason I'm testing this as opposed to a different kind of load is because it's going to be this exact hard drive that this power supply is going to drive, and nothing else except for the controller board. So what we're seeing here is critically important to the actual load it's going to drive. Recapping this particular power supply certainly beats buying a new old stock version. I actually found one, a slightly newer model, also made in the 1980s on eBay for a mind-blowing price. And it is true that you can find a more modern power supply replacement, also in the same compact form factor, which puts out 5 volts and 12 volts, many times at a higher current rating than the original. But the problem is most modern power supplies come with what's called a soft start feature that slowly ramps up the voltage instead of just immediately, bam, kicking out the 5 and 12 volt at their maximum voltages. And normally soft start is actually a good thing, but for this particular kit, it's not fully compatible, and it causes a little bit of glitching because the power doesn't go up to its maximum voltages quite fast enough. And that's not true in every case. For example, I have a video on replacing the power supply, the original Sony power supply of an SE30 computer with a modern version. In that case, soft start is not a problem at all. So be sure to check out my link to that video if you haven't seen it already. But what I'm just trying to say is that whenever you're replacing a very, very old power supply with something new, you need to take a little bit of care, not only that the voltages and current ratings are correct, but that the voltage ramp when you first turn on power may or may not be compatible. So you just have to watch out for that. And that's it for part 2 of this video series. Be sure to keep your eyes peeled for the final part 3 segment, where I will put this power supply and the associated 10 megabyte hard drive back in the original 1985 Macintosh from whence they came. I will also talk a little bit more about the history of this kit and show you how it operates and talk more about, well, what it's all about, the pricing, and so on. Towards that end, if you're not already subscribed, please subscribe, because that will allow you to then click the bell icon. When you do that, that will send you a notification whenever I come out with a new video. If you like what you saw today, please be sure to give it a thumbs up. If you have some thoughts to share, please be sure to let me know down in the comments section below. I read and reply to every single comment. Before I close, I'd like to offer my sincere appreciation to two very generous gentlemen who donated by PayPal to my YouTube channel in the month of February 2021. To begin, I'd like to thank George Tomasi, who lives in Paris, France, for his donation. George was telling me that he's a very modest collector of vintage Macintosh computers that were made from about the year 1989 through 2002. George also has a passion for beautiful and cleverly designed technology, which, in my opinion, very accurately describes Apple products. I'd also like to humbly thank Alex Buckland, who lives in the United Kingdom. For those other of you who also live in the UK, I should mention that Alex has his own IT support company, so if you're in need of those services, I have put a link to his company in the text description below. If any of you would like to join these two gentlemen in supporting this channel by PayPal, I have a PayPal link in the text description under each and every one of my videos. Also, the text description is usually packed with a lot of information. I always put an index there with timestamps that allows you to jump to different parts of the video. So if you do watch the whole video from start to finish, thank you. But it'll allow you to jump back to certain parts that you may find relevant so you can watch them over and over again. I also put purchase links, usually to Amazon USA, because YouTube tells me the majority of you who watch my videos are actually based in the US. And I will put things there that are relevant to each video, for example, a soldering station, flux, iso-alcohol, tools, and so on. And even if you're not based in the United States, a lot of the products can be found on Amazon's in different parts of the world too. I'd also like to mention that in each text description I have other things, such as links to reference materials, sometimes an old magazine, sometimes, well, things that I find interesting myself and things that I think you might find interesting. Sometimes there's links to software. So whenever you watch one of my videos, please be sure to expand out the text description and see what kind of goodies I have inside. Thank you folks for watching, and I wish each of you a wonderful day.